Okay guys, I'm in part 3 of the videos. This time, as you saw, we had no post-tension bars inside here. Bars, not tendons. So in this case, we're going to use some thread awl. And this was purchased for this project here. And so this is still loose. It's still loose. This is what it looks like internally. It's just a post-tension bar in there. For the retention area, I'm going to use just a nut. I'm going to push it up tight to there. And hopefully I can get away with doing that without tack welding it in place. I'm going to put a washer on this side, and we're going to nut it, and we're going to pull it taut. Yeah, I hope I have it kind of close enough to the inside wall of here to show that it can't slide. As you can see, hopefully I can open this up a little more. It looks like it's right there on the edge there. See at the edge, right where my thumb is? Right through there. It's hard to open now because the bar is actually stopping it from opening. Isn't that something? The thing they're discounting. So it's not welded at all yet. But you see I'm having problems even just opening it. And it's touching there, but when I close it, it probably changes just a little bit. Again, the bar is right there. The bar. So let's move on. Let's put this together and give you a shot. Okay, so I tightened it up. See the nut there? I tightened the rod up. Noteworthy is, you remember, I don't have concrete filling this whole thing here, so it's got some voided space. So as I crank on it and tighten it up, it does create a little bit of a slide because the concrete is not encapsulating the rod. It's concrete, an existing system that's concrete around the rod. Save the tube distance, the hollowness of the tube along with the rod. Let's talk about that hollowness of the tube. Let's consider this that I just talked about, how hopefully I had it tight against here. But it turned out it's going to work in our favor in theory and theoretical conversation, is that it's a bit of a gap. It was a bit of a gap because as I cranked it down, it did create the same cramp force effect of sliding the end until it hit the wall. I think it's hit the wall at this point. I think I'm just elongating the rod if I go any tighter. So the space might have been, this much. Hey, doesn't that space exist in the post-tensioning rod between, since it's not grouted? There's some space that exists there. So that could allow for some slide as they're post-tensioning, some clamp force to slide this over. I ground off the face of the tip of this. So if you can imagine where the tip was a moment ago in your videos, the tip is now gone. And we're talking, not even, maybe 1/8 of an inch, 1/8 of an inch. But now it can't elongate it. It can't go any further out, I think, because I maxed out. So I ground it, and now I'll test it without hopefully breaking this and not deforming the bottom, I hope. I hope it's not deflecting the bottom too much. Let's just turn it there and look. Yeah, so my baseline here is still tight. It's not going any further. So the rod is maxed out. Looking at the inside nut here, it doesn't look like it's deforming. It's biting in a bit, but not deforming too much. So even though I'm tightening it more, the rod, it's maxed out. So again, let's look at that edge. Now let me give it a couple more turns. So that's a quarter. Oops, definitely. I felt the. You guys know I do videos on bolts and all that on my other channel. That's done. That bolt is done. Okay, so now it's there. It can't go any further. Let's now add the clamp on it. I mean, no, don't add the clamp. Yeah, the clamp to see if I can get this to slide off. Let's add the load. So they said the clamp force is what's doing it. So I already have this one fully post-tension, if you will. The other one is out here. This would be 250 kips to 280 kips. Was it 280 on each of them? So this is 280 kips and that's 280. One part of the report says they both reached 280. Another one says this was at 280 and this one was at 250 and last cycle 30 kips that still need to be applied. Well, let's just say that this can't move anymore. Down here at 250 kips, the last 30 is just a little bump. It's not making it slide at all. Oh, I had to cut the bottom of this, guys, to access it, just so you know to do that for the bolt. So now I want to apply a load. The next, hold on. Okay, so what I did here was I had to cut the bolt to be able to turn this. Also in this video, I put the cranking end, the clamping end, if you will, the working station up top here as the bridge has it. I have it clamped down here, and we have the one bar that's set at the base. That bar's got 250 kips on it minimum and 280 maximum, or more depending on how the elongation went. They did not have, as reported by the one guy that's the only person, engineer, that is certified to certify the post-tensioning. He was not there the day that they post-tensioned. So, you know, VSL had no right to do it, and MCM had no right to do it, and neither did FIG had no right to do it without the guy that's certified, the engineer certified to authorize, to verify the post-tensioning, the kips. Okay, so much for that scheme, as the FIG engineer states. All right, so we have this now tight at the bottom. We have already preloaded it a little bit, and we have let's mark this. Let me do this. So I indicated this a couple of ways. I scored it with the saw blade, a grinder blade, without fusing it. I put an orange mark here, an orange mark there. And now let's go ahead and add some clamp force. And I'll add it while we watch it down here. So there's the handle position. And I guess I'll just add it here and we'll go down. Now we'll watch it here. I'm really cranking on this thing. I'm at a quarter turn. I'm afraid I'm just going to be crushing the pipe in a minute. Alright, so it just took a bounce. And I was expecting the back and forth torque action I told you guys about. See that? In the previous video I said the back and forth, that when they do this side and then this side, it creates a back and forth rotation. If you remember my other fig, I said like that. Now you see what I'm talking about. So now this one say this one now is a 280. This one now became loose, more loose, because this took 280, and that's that back and forth torque action. But you see what happened? We did get a slide, a deformation down here. But remember, for this to deform, this didn't change. This didn't buckle. So if this didn't buckle, that means the canopy, it has to be moving, crouching down. Crouching down. That would create that force I mentioned in a video about a year ago, even talking about, what happens when you're doing that? Are you creating a bending moment in the nodal area? Well, this would be the nodal area here, these two, without the luxury of having the spine, the canopy. But if I crank this too much, I can keep moving it out. Let's go ahead and see how far we can push this. I want to know if I can get this loose. It's still tight, this one down here. I want to know if I can push this one to some limits to loosen this one up. Let's crank it some more. At some point, I think it's just going to start. This in the case, this is what I talked about. Is just the clamp force probably just disintegrated the back part of 12. Remember, this would be the 12, but I haven't taken liberty here putting it in this angle. It should be back here. But this would be the back of 12, no longer being able to take that and disintegrating. It wouldn't have caused a slide. We know that because this was all cracked up on the other side. It would have buckled by then. This got some serious force in it now. Let's go ahead and continue. So the slide works on a non-buckled, on a non-deteriorated member, a structurally sound member. This is not structurally sound in the real deal. That's what I said. The one video, the one image they can't address. And that's that buckle, that cracking all on the back side of this. Let's go ahead and crank it up some more. Okay. Now I'm probably getting some deformation up here somewhere. Let me just keep cranking. All right. So I mean, I'm really cranking on it. It's not loose yet. Remember, I put this pretty tight. I'm looking to see if, so far so good. Trying to see where she's going to, probably got a lot of force down there now. Probably has an excessive amount of force going down there also. Let's keep cranking. I hear it creaking like something's ready to play a little funny with it. It's like it's backing out at the top a little bit. The torque action of this sliding it off a bit. Well, I'm maxed out. Let me pause it and try. Too bad I can't do this with one hand and keep it going, because I'm going to put 2 hands on this thing and crank it. Oh yeah, she's deflecting down here on the metal. A little bit. Let me tighten this up and try repositioning. So I'm still cranking on it. So far, this is what we've got. We've got this much movement. We're at that bar, and it just can't shear through it anymore. That bar is really holding it back. So I mean, we're only going to don't expect to see it slide off. You start seeing this crush now, because the bar is now stopping it from moving. It's not going to shear that bar if this sliding this over. This is your max we're going to get out of this, but the forces are still applied. Are going to just deteriorate the back of 12, as we know. But the forces on this, and that's why I said the back of 12 is the one that caused the failure, because this guy is already structurally shit. All right, so let's crank this some more. Oh yeah, we're maxed. I can't crank it anymore. Let me try. That's the position of the handle. Let me try it. Let me see if I can put this camera down for you guys and you can watch me try to make it break in front of us. I know the noise is tough. Sorry about that. It's on the angle I'm trying to set you up on. And I gotta look through there. Yeah, it looks like you can see the top of it. Okay. Let me crank this, see what happens. Remember, I can't turn it. I can't turn it beyond the bar. Excuse me. The bar is stopping it from sliding any further. The post-tension bar, the one that they discounted, said doesn't exist. It just doesn't exist in that formula. But that's the best I can get of sliding of that. And that would be excessive. Remember, it's going to be limited to the stirrups holding it back. There's stirrups all in this thing. Let me give you an idea. So the stirrups and concrete encasing this, and also another bar up top there. So that bar acts as a counter force also. The one above is also part of stopping this from wanting to slide. And it's only going to have the limited. So stirrups are all through this thing. Stirrups are going to make this act as one. They come all the way around. They come all the way around. And they encapsulate all the concrete. And so you can imagine the stirrups. Now the stirrups are in there, and here's the bar. So the bar has that little bit of wiggle room to move, and that would only be inside. There's the bar, only inside the duct. The size of the duct would only allow that much, and maybe I can find it and put it in comments how much the size of that duct is compared to the 1 3/8 pipe or just 1 3/4. This might be the one I don't know which one it is. I can comment on that. Doesn't matter. It's related to a duct. How much the max it will slide before it hits the concrete. The concrete hits the stirrups. The stirrups can't slide. It had to move 2 of these together. Remember, there's 2 bars. 2 bars, not 1. 2 post-tension bars, and they're both. The limited room is just that little bit. Just that little bit it could nudge up against, and that would be it. In this case, I have a little bit more room than that pipe than I thought as far as it before it hit the wall inside there. Now, for fun, if I only knew the ducts, I could put a straw around there. I could pack this with concrete, and then show you again. And this time, the slide would be a lot less. The slide would be a lot less than what we see now. But you guys get the drift. You guys get the drift of why the bar is so important. No matter how much I crank that now, that bar, this isn't failing. This joint is not failing. So if the joint is structurally sound, it's not failing. It's going to have that much slide in it. It's not going anywhere. It's not failing. It can only butt up to there, and it just won't go past the bar. It won't shear this bar. It can't move anymore. So that puts us back to number 12. Number 12 is what was disintegrated at the base of it. There is the the bar at it, the clamp down there just disintegrated that rest of the non-structural joint, if you will, as the forces were on it, disintegrated it. 12 just allowed it to drop down. That lost its whole integrity of the whole structure at that point. The whole structure lost its integrity then, but 12 is the cause. Well, the original cause is this whole bridge was going to fail anyway, right? It had potential. It was progressively collapsing from the beginning, with all these cracks indicating all these cracks in movement. But they try to tell you they were stable cracks. They're stable cracks. They were predicted cracks, but yet there's nowhere in the drawing shows predicted cracks. All right, so in the drawings, so now where are we now? And they were opening up, they were widening, and it was kept being a concern. But yet we don't see the responses back about why they're widening. In fact, Danny Pate says, I don't know why. So at that point, he didn't know why. He didn't know what was going on with the structure. If you don't know why the cracks are happening, you don't know what's going on with the structure. He should not have been ordering post-tensioning. The post-tensioning, the bridge, I told you how I explained it, that why it didn't collapse after post-tensioning was I believe it reclamped and that it held on. So if I were to loosen this clamp up right now, let's say I take this force off, right? So let's take the force off. Let's take it off. Let's watch the edge. All right. Did it go back? Well, what would make it go back? Why would it go back? Just because there's a spring in there? No, this is the new location now. This is just like we see in the drawings. We got a new location, new setup. So now you're going to add from here. You're going to now add 280 kips, and so now you just reposition. It's a new shape that you're now adding the kips to. So the bridge didn't get better after all this damage was caused by detensioning. But they thought they could recapture it, put it back in time, as I said in video over a year ago, that they thought they could put it back in time, and they couldn't. All right, I hope this helps you understand why this number 11, if it was structurally sound, why the post-tensioning bar doesn't allow for sliding, the shear. But I'm stating that this damn thing never even got the real forces on it. At least we didn't see it in that capacity. Maybe there's another video out there they're holding out on. But this should have buckled with all those forces in there. If I would have cut this member, crack this member up if it was concrete, and put all these cracks in it, and then put all that force on there, this should just buckle down here. I mean, it's not even, I guess you could say, I could still say theoretically. I want to say it's not even theoretical. It just should just buckle all apart because of the twisting in the structure. It already has a twist in it. As I talked about before, I said, hey, in the video before the release came out, I said, look at it. After the detention, it's twisted. So this bridge has a natural imbalance, I stated, a natural twist in the canopy. Twist, a natural torque. And then lo and behold, their Figs engineer puts out 20x, that 20x times, showing the natural twist in this structure. So it's not balanced in the post-tensioning. And interesting enough, the post-tensioning is all balanced though. Everything is symmetrical. So that means the twist still exists. You just put a symmetrical load everywhere, but the natural twist of this bridge still exists. So it has a torque in it. It was never balanced, and I don't get, It appears that Denny Pate was not the head engineer on this. He was the signer, but it appears Dwight and Manuel and Manuel. I can't get it. Manuel and Dwight are the head engineers. So looks like Denny Pate doesn't get a pass, but it doesn't, especially with him coming out there saying add post tensioning. And along with Dwight, I don't care. He doesn't get a pass with that. But it wasn't his original thing. But he was at the meeting, right? So I don't know. He handed off to Dwight and also Manuel. I can't get it. All right. So you guys see what happened here. Hopefully this helps you. I'm terminating the video. You ask questions. I can do more of these type of videos to follow up more. I do have another idea or suggestion that I can try to work in here, but I don't know if I want to do it. The time.